Hello, welcome back. So if you remember in our last video, we arrived at a point in which we could create this movie. So we created an animation in Python, which detailed how a sorting algorithm worked. In this case, it was quicksort. And then we outputted those frames from the animation, and then we created a movie with them using FFmpeg. Now, what we'll do in this video is we'll take this one step further and add sound. So the sound that you heard playing there was every time an element was accessed, whether it was read or write, sound would play. So if the element value is large, it would play a high frequency sound. If the element value is small, it would play a low frequency sound. So that's what we're going to go ahead and do in this video. So if we go back to our code, what we're going to need to do is we're going to need some way of mapping a value to a frequency. So the quickest way to do that would be to find some function. We're going to call it frequency. Yeah, we'll call it frequency map. We're going to give it a value of x. That will be the value that we want to actually create a frequency for. We need to give an x min. Give it a default value of 0. Give an x max. Default value of 1000, and that's because when we created our original array of values, we said anywhere between 0 and 1000. We'll give it a frequency between 120 Hz and 1200 Hz. And the function in this is really simple. So there's a numpy function called numpy interp, which basically says for an x value between x min and x max, remap that to a value between frequency min and frequency max. So for example, if x min and x max are 0 and 1000, and you give it a value of 500, and frequency min is say 0 and frequency max is 2000, it will return a value of 1000. It just remaps it. And the reason we've created a function for this is just because we're going to just use these default arguments here in the function, so that we only have to call a function with a value of x. Okay. The next thing we're going to want to do is we're going to want to define some more parameters. Let's go for audio parameters. We want a sample frequency. Let's go for the standard 44,100 Hz. We're going to create an oversample, which I'll explain later on why we need this. And that's that. So what we want to do now is once we've sorted this array and printed out some of the things associated with it, so there's not really a good way to play the sound while viewing the animation in Python. What we can do is create the sound file so that after we've created our animation frames, we can combine the sound file and animation into a video. So to do the sound file, we're going to need to import something from SciPy. So there's a package in SciPy called WAV file, and WAV file will allow us to write any data to a WAV file. So what do we need to do first? Well, the first thing we need to do is we're going to recreate our array. So we're going to create an array of the right length to hold all our sound data, and it could be quite large depending on how many numbers we're sorting and how many iterations it takes, but that's just one thing we have to put up with, and most modern computers should have more than enough memory to actually be able to do this. Let's go ahead and create an array. So we're going to create WAV data. It's going to be a numpy.zeros array, so it's just going to be full of zeros. It's going to be of length, so fsample times the length of the array values divided by the FPS. So this means if this is 44,100 samples per second, and this value here is how many individual frames they are, divided by the frame rate, so that's telling you how many seconds there will be in total. So that will then give us our total size of the array. We're also going to define a value called dn, and this is with the number of values in a chunk. So this is just the sample time, sample frequency, how many samples per second, divided by the frame rate, which is basically telling you how many samples are contained within a single frame based on this sample rate of 44,100 Hz. So they're the two variables we're going to need at first. And then what we need now is some way of creating chunks of frequency. So if you imagine something like this. So what we want to do is create something like this. So for example, if we're accessing an array element with a small value, it will play a relatively low frequency. Then if we access a large value, want to play a high frequency, and then the next element again might be a low value, so we want to play a low frequency, and we want some way of being able to place discrete chunks of that frequency next to each other with the length based on the chunk size that we've just calculated. Let's go ahead and do that. And to do that, we're going to want to have a way of actually determining the chunk number, basically, and also the value to which the frequency we need to play. What we'll do here is we'll enumerate the values from the array. Remember, the array.values is the magnitude of the value that's currently being accessed at index whatever, as determined by r.indices. And what we want to do is we want to know what frequency do we want to play based on that height. And we can do it very easily because we've just created the function frequency map. We'll create the frequency map and we'll just give it the value. And we know the value is between 0 and 100. And we know that it will return a frequency between 120 and 1200 based on the value of x. That's our frequency. We're then going to create a function which will take in that value of frequency and return a chunk of that frequency. So like in this example here, I want it to actually return this chunk. Let's go ahead and create another function. So what this function is going to do is it's just simply going to return a value. So let's say here, so y equals numpy.sine, so we'll create sine waves at the correct frequency, so 2pi times the frequency. And then we need to give it a linear space. And you'll see that we're giving it the delta time, so the 1/60th of a second, for example. And we want the total samples to be an integer. And we want it to be dt times the sample rate. So that's only how many samples in that chunk, which is the same number as the dn we calculated below. And then we're going to return y, return this value. So that should return the chunk required. Let's go back down to where we were doing this. So then we can go ahead and use that function. Call it sample. Sample equals freq sample. So we'll give it the frequency, give it the dt, we'll give it the sample rate. Okay, and then what we're going to do is where the wave data is. So wav underscore data, remember wave data should be the right length. We're going to say, okay, we know the size of the chunk is dn, so we're saying I times dn. So that will start at 0 and then go up in steps of dn to I times dn plus dn, remember that's the length of the chunk, is equal to the sample. I don't expect that to work, just for the last value. Oh, it did work. Let's have a look. So wave data, you see now it's populated with some wave data. And the good thing is about using Python in general is that we can literally just do something like plt.plot, and let's just plot wave data. And let's just do the first, looking at our variable explorer, which is another good part of Spider. We see that 735 samples make up one chunk, so one frame basically, 735 audio samples in a single image frame. Let's go ahead and just do the first 2 times dn. Plot that, and that should have opened a plot. Sorry, let's close those, do that again. Still playing this animation. Just comment out this animation for now. Go ahead and run this again. Type out the command, plot wave data, and remember we need to go from 0 to 2n. And there we are, we can see we've done it correctly. So within this 735 samples that will be playing during one visual frame, we can see that we had a high frequency and then a low frequency. If we want to go in, we can see from our tracked array, we can go in, go to the values list, click it. We see that the first value that accessed had a value of 414. The second value that was accessed had a value of 69. So it should be high frequency then low frequency, which is exactly what we're getting there. So this seems to be working. What we can do now is we can save that. So this WAV file package from SciPy has a convenient function which allows us to save it. So let's do this. Write, so write is the function that will write it. We'll then give it a file name and we'll call it sorter. So remember, sorter is the variable that describes the sort. So this, for example, will come out as quick. So this will be saying this file is going to be called quick something. And the rest of the file, let's go ahead and call it underscore sound.wav. And then the good thing about this function is that it does rescale the sound so that the maximum amplitude of the data array becomes the maximum amplitude of that particular sound format. And when we run that, we see that it worked. We go ahead and look at our folder, and it's created a sound here called Quick Sound. Go ahead and play it. Now that didn't sound very nice at all, and there's a very good reason for that. If we just go back, I've done an example of this. So where we created our sounds, we have different frequencies, and the problem is this is done in chunks, so that when that chunk is played, it can stop very abruptly. So you see here, the sound was actually going from a positive value to a negative value, but then stopped, and immediately when stopping, a sound of a high frequency started to play, and that sound, it was actually going in the positive direction, so it was going from negative to positive, and there was a discontinuous jump. So if you imagine now joining these audio files, you end up with a sharp jump between these two samples. And if I go ahead and load up Audacity, and I'll put the sound in here, let's go ahead and have a look at that first section. You can see it playing a nice sine wave, exactly what we wanted at one particular frequency, but then we had a discontinuous jump when the next chunk played. And likewise here, you get a particularly nasty jump here. I originally thought of two ways to solve this. So the first way would have been to take this and then run a low pass filter over it with a particular frequency in order to try and sharpen out these discontinuities, but that didn't actually help much. You still could hear some faint crackling. Now the better way to do this would be to add, or you could add something like reverb, and that's basically the approach that we'll be taking. And so we're going to have to do something called blending. So here what we do is, rather than have these discrete frequencies, these discrete waves that are then joined at the start and end point, we actually allow them to overlap. So now we've allowed each frequency to extend. So where it previously stopped here, we've actually allowed it to extend. But more importantly, we decrease the amplitude as it extends beyond its chunk size. You see here the blue curve, so the blue frequency, the low frequency, goes to its maximum point and then continues, but with a decreased amplitude, and that's just linearly decreasing amplitude. Likewise, the frequency in the middle, so the orange frequency, during its chunk, it has the full amplitude, but then outside, it has a decaying amplitude that allows it to extend, and likewise for the green frequency. And then when you add all those up, you end up with something like this, which is a much smoother curve than we had. So there's no sharp discontinuities in here. Everything's quite a sharp curve. We do get the situation where you can have amplitudes greater than 1, and that's just because we're summing up potentially up to 2 basically, because we're summing up different sine waves, but that's fine because it just means that when two elements are accessed or there's an overlap, it just plays both of them at the same time with the same amplitude. But this is the approach that we're going to be taking. So we're going to actually be blending these audio files together, blending these audio chunks together. So I'll go back and I'll just call this Quick Sound Horrible. Not very nice at all. Then we go back into our code and we're going to add some things to make this better. So for example, we're now going to implement some oversampling. So the oversample is basically just going to say, if I have an audio chunk with, let's say, 100 elements, an oversample of 2 is going to mean, all in all, I'm going to have 200 elements with 50 elements to the right, 50 elements to the left, continuing the sine wave, but then decaying to 0 over that distance. So it means that each chunk will overlap with exactly half of the next chunk, and likewise the chunk after that will also overlap with that chunk. So any one time you'll have 2 audio frequencies playing, assuming that all 3 are different. If they're the same, then they just overlap normally. And let's go ahead and implement that. So where we had our function here, so frequency sample function, let's think carefully about this. So we're going to implement oversample, give it a default value of 2. And then in this function here, we're going to do something like this. So we're going to say we need some mid samples. So this is the sample to which the amplitude is 1, basically. We need some padded samples. So this is our oversample. So this basically means, for example, 100 element chunk would be 50 on the right, 50 on the left. And then we need our total sample, so the actual total samples which that sound takes over. And then we're going to do something very different. So if I just copy and paste in. So what it's basically saying here is that we create our sine wave. So this entire sine wave is in the same place as before, but now it extends over total samples. So rather than being 735 elements long, it will now be double that, so 1470. So we're going to create the sine wave, but then what we're going to do is for every sample up to the padded sample, so the first 735 doesn't divide by 2, but this is fine. It just means that we might have one sample either way. So it's not strictly the middle 735 samples. It might be the 734 samples, for example. It might be shifted left or right by one sample, which 1 in 700 doesn't really make that much difference. It's basically saying every sample up until the middle chunk basically is now multiplied by a function that goes from 0 to 1. So it's linearly increasing, so it gets louder as it goes towards that middle chunk. And then every sample that goes from the end of that middle chunk to the end of the overall sample is a linear decay from 1 to 0. So you get this sort of trapezoid function that's multiplying the sort of oversampled sine wave. And then we need to go back into our wave data at the bottom, and we need to make some more changes. What we need to do here, we need to take a look at these indices. So what we need to do is we need to calculate some indices. So we need to say, where is this sample size from? So for example, 735, the first chunk needs to come along. You need to say, okay, it's 735 plus some oversample. So it's 735 plus double the oversample. So we need to implement our oversample into our function. Call that oversample. Okay, so that will now return an array that's much bigger. What we need to do now is determine the extent of that array and where we need to put it. So for example, if we have our 735 elements from our original sample and we've oversampled by 2, what it means is that this sample needs to change. So here I've hard coded it for an oversample of 2. We can always go back and change this to try and find the correct sample size. I'll do something a bit more fancy, but for now, let's just hard code it as if it's 2. Now we need to find the 2 indices. So the first index we need to find is the index on the far left. So what we do there is we say, okay, we're initially we have I times dn, which remember dn is the sample length, so 735 samples. We'd say, okay, where is half of that value? It finds that, and then it minuses half of the sample from that. So where you start here, find the half, and then you minus half the sample from that. It takes you outside, but that correctly takes you to the beginning of where that sample needs to play. And likewise, the next index is simply going to be that first index where we know the sample needs to play, all the way across the full length of the sample, and that will neatly go over so that the middle portion of that sample is at the chunk it needs to be. And then we need to reflect that in our wave data. So remember, we've already created our wave data array, and that was initialized to 0. We then say, okay, let's actually add on our sample at that particular point. And then we do this, and it won't work. But the problem is that it's not going to be able to find this because the arrays are not the right size, and particularly this first value. So you've got to think that we're trying to add a chunk at the beginning, but then we're saying actually add it to this minus index. And likewise for the end, try adding on data to the array that doesn't exist. So we'll put this in a try catch statement. What this does mean is that we will lose the first sample and the last sample, which out of say 700 samples, or however many the sorting algorithm takes, could be 1,000. I think that's a reasonable loss. We could add more functionality in here to actually enable it to do the first and last element properly, but we're not going to do that. So we do a try except, and we'll just print out so we know that it had an exception, and we should just see 2 of these appear when we run this function. So there we are. Failed to generate the 0th index sample. As expected, it can't place a sample that's too big where the array doesn't exist, and likewise for the last sample, it also can't place that sample beyond the limits of the array. So that now should have worked. If we go back to our original sound, so I'll let you listen to what it was before. Absolutely horrible crackling, and now what it sounds like with the blending. You've got to agree that sounds much nicer. So that blending has helped perfectly. It sounds much more realistic. And you notice now we've outputted frames, which is our image frames, and we've also outputted our sound associated with that. Okay, so now let's go ahead and create a batch file that will just have the necessary FFmpeg command in order to generate a video in which the sound and the video are combined. Here's the command I'm using, so don't get too disheartened by the look of it. All we've done is said, let's set a variable called S2, so just call it quick because obviously we want to maybe compare quick sort and insertion sort. But then it's the same command, FFmpeg, reading each individual image frame. This time I've used the percent operator in order to insert this. So where it says %s2%, it will be inserting the word quick. So it's going to find in this folder called frames, something called quick_frame. Then I'm going to look for a 0 padded 5 width number, which we know the number of the frames goes between or follows. We then give it a second input, which is the sound, so quick_sound. We then tell it again to use our H.264 encoder with a very slow preset. We're now telling it to use an audio codec, the AAC codec. We're going to give it a constant rate factor of 0 again. But the two important commands here are map 0v and map 1a. This means map the video from input 0, which is this one, input 0, the first input. Map the audio from the second input, which is the sound. Map those together and call it quick_sort.b4. I'll go ahead and just run that in Notepad++. And now we see it's created a video called quicksort.mp4. And we've done it. So that's it. So that's basically the end of this tutorial. So we've successfully done several things. So we've implemented a sorting algorithm. We've successfully created an animation in which we've basically tracked all the elements that have been accessed, either been set or gotten. We then created the animation frames. We then turned those frames into a video. And simultaneously, we've created an audio file from the information about which element was accessed. So if the array element had a large value, it would play a high frequency. If the array element had a small value, it would play a low frequency. We successfully put those into an audio file with some blending between the frequencies to avoid popping and crackling. And then we've successfully combined the audio and image frames into a video and created a nice animation. And this is the sort of thing you see on YouTube. Sometimes see them called the sounds of sorting. And so this has been an adventure. I hope at least some people have found this insightful, enjoyable, and this is exactly the sort of process you'll go through when creating animations in Python. And so yeah, you can do this for a lot of different things. You can do any sort of algorithms. You can do something like this to be able to actually visualize what it's doing. It's always nice to see exactly what it's doing, because just by looking at formulas, it's not always obvious. If you're lucky, you'll go on Wikipedia or online, you'll find someone else that's actually done one of these animations for you to visualize how it's done. But if one doesn't exist, you can always just crack open your Python, start coding and get the animation yourself, and you start to really learn more deeply about what's actually happening. So yeah, thank you for watching. Hope you enjoy this, and I'll see you next time.